So again, to reiterate what we've been talking about this whole unit, all relationships can be expressed in words of mathematical calculation or equation in tables and graphs. Okay? Linear relationships can be characterized by a constant rate or an angle and position. And we're for now sticking with the starting position. So when we look at these relationships here, so it says find the rate of change of the temperature if the temperature changes from 22 degrees Celsius at 5 minutes to 34 degrees Celsius at 10 minutes. So what we're looking for is some rate of change, okay, or a constant rate to give us the angle, and some starting position to be able to fix that line into place. So it's been given to us in words. We're being asked to come up with the equation for this. Okay, so what we want to do, and what's going to be the easiest to do, is figure out what is the slope. Okay, if you need a picture to help you with this, we can sketch a diagram. 5 minutes is 22. 10 minutes it's 34, maybe somewhere around there. Okay, and it's going to have some pattern that looks like this. What we want to find first is our slope. Okay, and our slope is going to be in our slope triangle. That's what we're looking for. And it's going to be our change in y compared to the change in x. So here the change in y, the end position is 34 degrees. The starting position is 22 degrees, so we went up 12 degrees. Okay, the change in x, we went from 5 minutes to 10 minutes, so 10 minus 5 gives me plus 5 minutes. Okay, the slope formula looks like this: y1 minus y2 over x1 minus x2. Okay, so we end up with 12 degrees Celsius over 5 minutes. Okay, now if we want, we can convert that into a unit rate, which is 2.4. Remember that unit rate becomes our multiplier, but remember that it is still slope, so it's being compared to something. Okay, and it's going to be compared to 1. So it's 2.4 degrees Celsius for 1 minute. Okay, so we've got the first part of this, which is slope. So I'm going to write my equation. Okay, so the temperature is equal to 2.4 times the time plus some constant we're going to call B, or starting position. So to calculate the starting position, we can use a property that any coordinate pair of degrees Celsius and minutes should fit into this equation. Okay, make sure you put it into the right way. But here we're going to I'm going to use 22 degrees at 5 minutes, and I'm going to plug it in. So 22 degrees, 5 minutes. Okay, and that's going to be plugged into our equation. So that's going to be equal to 2.4 times 5 plus b. So 22 degrees is equal to, in 5 minutes, if we go up 2.4 degrees per minute, we're going to go up 12 degrees. Okay, so the starting temperature, if we went up 12 degrees, if I go back to 0, my starting temperature must be 10 degrees Celsius. So I have my equation then. The temperature as a function of time, I'm going to put down minutes, m is my time, okay, is going to be equal to 2.4 m plus 10 degrees Celsius. Okay, so starting at 10 degrees Celsius, we're going to go up 2.4 degrees every minute, and it'll give us these points on the graph. Okay, and the units of change, okay, and I make sure that you're able to state the units of change. It's going to be always the y compared to the x. So it's going to be degrees Celsius per minute. Okay, that's going to be my units of change. And my slope is going to reflect that units of change. Okay. All right, so this problem here, we've got a hiker going up a hill. Okay, they're going up some hill. Maybe I'll draw it in this way. They're going up a hill, and they're going up at a rate of 38 meters per hour. Okay, so that's important. There's a rate there. Okay, and they're at an elevation of 380 meters after 3.5 hours of hiking. Okay, so I'm just going to sketch this as a graph actually, not as a picture. So at 3.5 hours of hiking, they're at 380 meters. Okay, and they're going up at 38 meters per hour. So that's going to give us, so we have some point that we can start at, and we can actually go back to 0, okay, using our rate. So we can go back 38 meters for 1 hour, another 38 for another hour, another 38, and then half of 38, and we can get back to 0 time. Okay, so that would definitely work. We can use our graph to do that. We can use a table to do that. However, if we recognize that we've been given the slope, so we've been given, I'm going to say my elevation is equal to, that 38 meters per hour is going to be my slope. It's the right units, meters, meters, and I'm going to times this by hours, times h, so number of hours. Okay, actually I'm going to make sure I put my units in there because those units are really important to keep track of. Meters per hour times the number of hours, okay, plus my starting position, which I'm going to call B. So I just need to figure out my B. Okay, I'm just going to change my color here. That's my B, and that's going to be my starting position right there. So I just need to get back to 0. I can do it using my slope if you wanted to. Okay, I can use a slope on my graph and just say, well, negative 3.5 hours, I need to figure out how far I go down. Or I can just do this algebraically by plugging in my coordinate pair. 3.5 hours, elevation is 380. So I get 38 times 3.5 plus B. Okay, in 3.5 hours, okay, when I do my calculation, okay, 3.5 times 38, well, you're going to have to do some mental math here. So 76, 106, 114 plus 19 is going to be, I'm getting 133. Okay, let me just double check that. So 38, yeah, 38, 18, I think that's correct. So we've gone up 133 meters, okay, in 3.5 hours. Okay. Okay, so we're going to end up with, so when we look at this problem here, then if I take a look at my graph here, so I need to actually go down 133 meters to get back to 0. And notice that algebraically, we end up going backwards. So when I solve for B, B is equal to 380 meters, and I'm going to take away that 133 meters of change. So this portion here represents the net change. Okay, so there's my net change, there's my net change, and I'm going to take it away if I'm going to go backwards. And that's what happens when I put it to the other side of the equation. In all said though, we're basically solving for B. So B is equal to 247 meters. Okay, so the starting point at 0 time, the starting position is going to be 247 meters. In 3.5 hours, I went up 133 meters and I ended up at 380 meters of elevation. Okay, so my equation then looks like this. Elevation as a function of time in hours is equal to 38 times hours plus 247 meters, or y equals 38x plus 247. Okay, so those represent my equations for those lines, for those relationships. Okay, so this one here, we've just been given the relationship as coordinates. 2 over 4 up, 5 over 8.5. No, we got some line that looks like that. I need slope. Okay, so I'm going to start at 4, end of 8.5. So that change in y is going to be 8.5 minus 4, which is positive 4.5. My change in x. Okay, I'm going to end up at 5. I started at an x of 2, so I went to the right, plus 3. Okay, my slope definitely looks positive. Slope is equal to 4.5 over 3, which is equal to, I'm going to use a unit rate of 1.5. That's the multiplier in my equation. So I end up with y equals 1.5x plus b. Now to solve for b, I can go use my table and use slope on my table. I can use slope on my graph, or I can plug in y and x pair, because y and x pairs always can be plugged back into the equation. Okay, and it's never wrong. Sometimes it doesn't tell us anything interesting or useful, but it's never wrong to do. Okay, so when I plug it in, those points on the graph must fit back into the equation. So I end up with 4 equals 3 plus b. When I solve for b, b equals 1. My drawing's not super accurate, but it looks like it's above the x-axis. So my equation, my line becomes y equals a slope of 1.5 times x plus a y-intercept of 1. There is my equation of a line.